Okay, let's talk about another gas law. Let's talk about Charles' law. So Charles' law deals with volume and temperature. So volume needs to be, or is most commonly in milliliters or liters. And it just means that our first volume and our second volume just has to be in the same unit. So both either milliliters or both in liters. The T stands for temperature, and temperature in chemistry has to be in the Kelvin scale. So the Kelvin scale is used because it goes all the way down to absolute zero. And absolute zero is when the theory is that everything would stop moving. So just to give you an idea of the values for absolute zero, at absolute zero, which is 0 Kelvin, our Celsius would be a negative 273 like we see down here. And our Fahrenheit value for 0 Kelvin is a negative 459.67. So I don't know about you, but I don't want to experience that temperature. That's pretty low, almost a negative 460. No, thank you. Okay. Here is your equation for solving for temperature. So if you ever have Celsius, you're going to add 273 in order to equal Kelvin. Make sure you know this for the test. And if you need to, you can always just rearrange your equation and solve for Celsius. But this is the one I would know. Okay, let's talk about proportionality with volume and temperature. So with volume and temperature, if volume is on my y-axis, temperature is on my x, here's what it's going to look like in a graph setting. So this means directly proportional. Another name for this would be, like if you were to name the graph, it would be just called a straight line graph. But volume and temperature are directly proportional, which means that if we were to plot any kind of point on this graph, say we plot 3 different points, okay, every time we look at the correlating volume and temperature on these points, we can see that as the volume increases, so does the temperature. And as the volume decreases, the temperature decreases as well. Okay, let's look at some visuals. So first visual is we have a balloon. This balloon started at the same size, same amount of volume. In this example on the left, the balloon is in an ice bath. So the temperature is obviously decreasing. On the right, this balloon is on a hot plate. So we are increasing the temperature in this example. And then notice the size of the balloon compared to each picture. With the lower temperature, the volume is decreasing. With a higher temperature, the volume is increasing. So again, we're seeing direct proportionality in Charles' law. Okay, here's another picture for you. You can pause the video and look at this if you'd like to in more detail, but what I want you to notice here are the balloons volume corresponding to the temperature. Again, it's increasing, so if the temperature is increasing, the volume increases as well. Think about an inner tube in the summer. When it's warm outside, your inner tube, the volume of your inner tube, it gets nice, and the gas expands, it gets nice and tight. Okay, if it gets cold or you put it in a colder body of water, then the molecules condense, and so that makes your inner tube a little more floppy. So think about that example. Okay, here are some examples that we're going to use. Let's go ahead and read the example, and as I read it, I'm going to go ahead and underline variables. And I think this is a really helpful technique whenever you're doing any kind of problem, because on a test, it's not going to say Charles' law, or most likely will not say Charles' law. So you have to figure out which gas law is being used, and you're going to learn 3 different gas laws. So you need to make sure you know which one goes with which based on what variables you have and how many variables you have. So let's start. A sample of nitrogen gas occupies a volume of 7.3 liters at 27 degrees Celsius. What volume will the sample occupy? So there's our volume at 180 degrees Celsius. Okay, now that we've got this underlined, we've got 4 variables. So we could think, this could either be Boyles or Charles. But we need to look at what is actually given. So let's go ahead and assign variables to each of these, and to each of the underlined items. So first one is 7.3 liters. Liters is a unit of volume, so we're going to call this V. And we also have a V here. So we need to decide whether we want these to be 1s or 2s. Again, it doesn't matter as long as the correlating variables go with that variable. So let's just make this one a V1. Notice how it says at here, which means this, which is degrees Celsius, is going to be temperature, has to be a T1 because these two correlate, the 7.3 liters and the 27 degrees Celsius, which means that the second volume needs to be just that. It needs to be V2, and it correlates with this 180 degrees Celsius, which is a second temperature. Okay, now that we have our variables outlined, we see that we have 2 volumes and 2 temperatures. So we can safely say this is Charles' law because there are 4 variables, 2 volumes, and 2 temperatures. Okay, before we start, we need to make sure that our variables are correct. So with volume, our units and our variables, it's liters, which is just fine, and this is our unknown, so we're okay with that as well. Our temperature, notice, is in Celsius, but in gas laws, your temperature has to be in Kelvin. If you do not put this in Kelvin, you will get the wrong answer. So remember, Kelvin is Celsius plus 273. Okay, so we're going to go ahead and add that. So 273 plus 27 is 300 Kelvin. So that's going to be this right here now. We're going to have 300 Kelvin for our T1. And then for our second value, we have 273 plus 180 Celsius, which is going to give us 453 Kelvin. So that's our second value, 453 Kelvin. Okay, now that we have everything in the correct units, we're going to go ahead and plug everything in. So here is our equation. V1 divided by T1 is equal to T2 divided by T2. Okay, so first volume, we've got 7.3 liters over this 300 Kelvin, it's our T1, equals our unknown volume, which is V2, and that is all over 453 Kelvin. Okay, from here, it's just a math problem. My suggestion is to cross multiply, but you can do whatever makes you more comfortable. If you want to manipulate your equation and get the variable, which is V2 alone, do that. If you want to cross multiply, do that. Whatever works best for you. So right here, we're going to go ahead and cross multiply. So we're going to get V2 multiplied by 300 Kelvin. Then we're going to cross multiply the other side. So that's going to equal 7.3 liters. We're going to multiply that by 453 Kelvin. Okay, now what we need to do is get rid of that V2, get it all by itself. So mathematically, we're just going to divide by the 300 Kelvin on both sides. Okay, when we do this, it cancels out the 300 Kelvin on the left. On the right side, the important thing is that it cancels out our units. It's canceling out our Kelvin, and we're left with liters, which is a unit of volume, so that correlates. So let's go ahead now and just do our math. So our math now is 7.3 liters times 453 divided by 300. And so our unknown volume with that math being calculated is 11.02 liters, and that would be our answer. Okay, if you want to check this answer, put it into the original equation. So we would go ahead and put it right here. And then you would divide these two values. And then you would divide these two values. And as long as they are the same with the exception of rounding, then your answer is correct. And again, you can look at your original values and determine if it's following the proportionality of Charles' law, which is direct proportionality. So right here you have 7.3 liters. And 300 Kelvin. Right here, your volume is increased from the 7.3, so it's 11.02, which means our temperature should also increase, which it does, and increases to 453 Kelvin. So this is showing direct proportionality, so you can feel good about your answer. Okay, let's do one more equation example. Okay, right here, a sample of hydrogen occupies 473 liters at 512 degrees Celsius. At what Celsius temperature will the volume occupy at 2,733 milliliters? So this is another value. Okay, let's go ahead and assign liters. That's definitely volume. At degrees Celsius, that's temperature. So we're going to make these ones. Celsius temperature, that's our second temperature. So that's our unknown. And then that correlates with this 2,733 milliliters, which is our V2. Okay, now let's look at our units. Our volume is in liters and milliliters. This is not okay. We have to choose one of them. It can't be both. So let's go ahead and convert milliliters to liters. When you do that, it's 1,000 milliliters in 1 liter. So we're going to divide by 1,000, which is going to be 2.733 liters. And then our temperature, remember, it has to be in degrees Celsius, in Kelvin. So we're going to go ahead and add 273 over here. 512 plus 273, 785 Kelvin. Even though this asks for Celsius temperature, you have to go ahead and convert it into Kelvin. Okay, now that everything looks good, we're just going to plug in all of our values. So we're going to do 472 liters. Remember, this is V1 divided by our T2, which is the 785 Kelvin. That's going to equal our V2, which is 2.733 liters, divided by our unknown temperature. Okay, once again, I would cross multiply. Whenever you have unknown values that are in your denominator section, they're tricky, so be really careful. Okay, cross multiplying, we get 7.85 Kelvin. We're going to multiply that by the 2.733 liters. That is going to equal 472 liters divided by T2. And then we're just going to get the temperature by itself. So we're going to want to divide by the 472 liters on both sides. And at this point in time, if you've made any mistakes with your units, they're going to come out. So make sure that you're writing your units down. So notice that liters cancel, and the 472, of course, cancels. Over here, your liters cancel, and you're left with Kelvin. Right here, if this doesn't cancel, you know that you need to go back and fix things. So just always put your units in these problems. Okay, now we're just going to multiply 7.85 times 2.733 divided by 472, and that is going to give us a temperature of 4.55 Kelvin, but the answer wants it in Celsius, and so now you're just going to have to use your equation for temperature. So remember that Kelvin is degrees Celsius plus 273. We're trying to find Celsius here, so subtract 273 from both sides. So now we get Kelvin minus 273 is going to equal our Celsius. So let's just plug in our number over here, which is 4.55 minus 273. And that is going to give us a negative 268.45 degrees Celsius. Ew, burr. All right, so if we plug this number back in, this negative 268.45, but you'd want to make it, when you plug that back in, make sure it's in Kelvin so that you have the right units you can check. So when you're doing that, make sure you're plugging in the right unit. Sorry, I don't want to throw you off. So when you're double checking your answer on this one, plug in this 4.55, and that should make sense. And make sure both sides are equal if you're double checking your work. And again, if you look at your values here, 472 liters over 785,